All right, so this video we're going to look at rational exponents and radicals. All right, so let's go ahead and get started. It's going to be a long video. So we got definition, nth roots. So if n is a positive integer and a to the n equals b, then a is called an nth root of b. So here's a few examples here. If a squared equals b, then a is a square root of b. And if a cubed is equal to b, then a is the cube root of b. All right, so let's look and see what that means. All right, so here we've got some examples here we want to evaluate. So here we have the square root of 49. All right, this is a radical, and the part B, we got the cube root, and here we've got the fourth root. You see this little number here, this 3 and this 4. That's called the index of the radical. So this is a cube root, fourth root, and then here you see there's not a number there. Well, that's understood to be a 2 for square root. So basically what we're doing here is we look at this number underneath the radical symbol, and in this case it's 49, and I'm looking for the square root. So I want to know what number can I square to get 49. Well, that would be what? 7, because 7 squared is 49. Now, something I want you to think about, what it says up here, if a squared equals b, then a is a square root of b. All right, so 7 squared is 49. Well, what about negative 7? Because if I square negative 7, I get 49 also. So would the answer be just 7, or would it be plus or minus 7? Well, the answer is just 7. All right. So whenever you have a radical and the index, okay, see here the index would be a 2, here the index is a 4. When that index is even, an even number like 2, 4, 6, 8, and so on, then this radical symbol means they want the principal root. And so what does the principal root mean? That means they want the positive answer only. Okay? Now, so that's why it's only 7, and it's not plus or minus 7. It's just 7. Now, here we have an index that's 3. So we just talked about if the index on the radical is an even number, we want just the positive answer. Well, if the index on the radical is an odd number, then it can be plus or minus. It doesn't matter, okay? Because, for instance, in this case, we want the cube root of negative 27. Well, what number can we raise to the third power to get negative 27? Well, that's negative 3, because negative 3 cubed is equal to negative 3 times negative 3 times negative 3. And negative 3 times negative 3 is 9, and 9 times negative 3 is negative 27. Okay, so just remember, if the index is an odd number, you can get a positive answer or you can get a negative answer. But if the index is an even number, then your answer is going to be positive. Okay, see, like for instance here, if we had the cube root of positive 27, that would be just 3, because 3 times 3 times 3 is positive 27. 3 times 3 is 9. 9 times 3 is 27. Now, what about this one? The fourth root of 16 over 81. All right, so instead of looking and saying, okay, what number can I raise to the fourth power to give me 16 over 81? Well, just do them individually. So what number can I raise to the what number can I raise to the fourth power to give me 16? Well, that would be what? 2, because 2 to the fourth is 16. and then that's over, and then what number can I raise to the fourth power to get 81? Well, that's 3, because 3 to the fourth is 81. And so this answer would be 2/3. Okay? All right. So let's look at this. What if we have an exponent of 1 over n? So if n is a positive even integer and a is positive, then a to the 1 over n denotes the positive real nth root of a and is called the principal nth root of a. All right, that's what I just talked about earlier. If n is positive, okay, if n is positive, then that notes the positive real nth root of a and is called the principal nth root of a. That means, okay, they want the positive. If n is a positive odd integer and a is any real number, then a to the 1 over n denotes the real nth root of a. And if n is a positive integer, then 0 raised to the 1 over n is equal to 0. All right. So what we have here is we have a raised to the 1 over n. And what we can do, we can look at that the same way as that. That's the same thing. What this is doing, this is taking this term here from exponential form and converting it to radical form. Okay, it's just a different way to write it. Going from exponential to radical, or you can go from radical to exponential form. This right here is going to come in handy later on in the lesson when we get to some other problems where it's going to help us to convert it back and forth. Okay. All right. So now if we look at this, so this is kind of like what we did earlier. So we've got 4 to the 1/2. Okay. 4 to the 1/2, then that's the same thing as the square root of 4. Okay, so all that's happening, you can see here, is that when you have it in exponential form, you see this denominator here, that becomes the index of the radical. Okay, and in this problem, our denominator is 2, so that 2 becomes the index of this radical. All right, and remember, if the index is 2, well, we just don't write it. That's square root. And so the square root of 4, we know that's 2. And this would be your answer here. And what about this one? Well, if we convert it to radical form, that's the cube root of 8. And so now, what can we raise to the third power to get 8? Well, that would be 2. And then the next one, that's what? That's the cube root of -8. So what can we raise to the third power to get -8? Well, that would be -2. Because -2 times -2 is 4, times -2 is -8. Now this one, we have the square root of -4. All right, so what can we raise to the second power to get -4? Well, nothing, right? Well, there is something, okay? If you're in college algebra, some of you may remember, well, yeah, I can do 2i, but we don't know about, at this point in the class, you don't know about imaginary numbers yet, okay? So what we would do here is we wouldn't put no solution. For this, we would say not a real number. All right. There is an answer, but it's not a real number. It's an imaginary number. Okay. And that's for a lesson a little bit later on. The lesson on complex numbers. I'll have a video on that. You can check it out if you want to. All right. So now we have a rule. If a is a real number and m and n are integers, I don't know why I wrote r twice, are integers for which the nth root of a is real, then a to the m over n is equal to the nth root of a all of that raised to the m, which equals the nth root of a to the m. All right. So what this is doing is this is telling us how to go from exponential form to radical form. All right, so you see two different things here, okay? Basically what this means is a to the m over n is equal to the nth root of a to the m, and we have a to the m over n is equal to the nth root of a to the m. Okay, both of these are true. All right, and then don't forget from the previous example, we also have this. All right, these are your formulas right here to go from exponential to radical form and radical form to exponential form. Okay, now as far as these two go, you might be thinking to yourself, well, which one do I use? Okay. Well, you use the one that's easiest to use for whatever problem you have. All right? And I'm going to show you that in this first example here, this 27 to the 2/3. I'm going to show you what I'm talking about there. We're actually, for part A on this example, we're going to work it two different ways. We're going to do it this way, and we're going to do it this way. We're going to use each formula, and I'm going to show you what I'm talking about when I say use whichever one's the easiest. Okay, so let's go ahead and evaluate this. So first, let's use this one. Okay, so if I convert this, that's going to be, now you see what we have here? You see the numerator of the exponent, that's this exponent out here, and the denominator here is your index on your radical. So this would be the cube root of 27 squared. All right, see, this is m, this is n. There's m, there's n. So now we have the cube root of 27, which that is what? 3. But remember, that's still squared, so that's 3 squared, which equals 9. All right? And that's all we're doing. We're taking this, we're converting it to radical form, and it makes it easier for us to evaluate. Okay? If you end up taking more math classes like calculus and stuff like that, you'll get to where you can just do that in your head and you won't even need to rewrite it. Okay? But for right now, I would say let's, go ahead and rewrite it like that. Now, I told you I was going to do it a second way also. So let's look at this same problem. But this time, let's put it in, write it like this, where the exponent is underneath the radical. You're going to get the same answer, okay? You're going to, I'm sorry, that shouldn't be a 3 there. It should be a 2. You're going to get the same answer, but look what happens. You see that? Right off the bat, you can see that using this formula was a lot easier than what we come across here. So because first off, we have to square the 27, don't we? You see that? You've got to square this 27, and that's 729. So, squaring the 27, that's not really that bad. You could write it there real quick, multiply it out, and get 729. But now the problem that you have is, well, what's the cube root of 729? Well, it's 9. Now, would you have known that? Probably not. I wouldn't have known it. Okay? The only reason I know it's 9 is because I know we already solved it up here. So whenever you're simplifying these things like we're doing in these examples here, I'm going to say probably 99% of the time it's going to be easiest to use this formula right here. That's probably going to make it the easiest to solve. Okay? I'm not saying that sometimes that one's not going to be easier to use. It may be. But what you have to do is you've just got to you've got to practice these things, and you practice enough, and then you'll be able to see, oh, well, I'm going to use this one because it's going to be easier, or I'm going to use this one because it's going to be easier. Okay. All right, so let's look at the next one. So we've just got these that we have to evaluate. So let's go ahead, convert it to exponential form. So that's going to be the cube root. Remember, the denominator, that's the index, and then I've got the -8, and then all of that is raised to this numerator here, 2. All right. And so this is going to give me what? The cube root of -8 is -2, and then that's squared. And so -2 squared is 4. And there's your answer. All right. So what about this one? Well, let's look at this one. We've got a negative exponent. All right. So the section before this one is about exponents, and in that section it tells us how to make exponents positive. Okay. So if we look at this as being over 1, okay, look at it as being over 1, then remember to change the sign of the exponent, we just move it across the denominator. Okay, move it across the denominator. So this is going to give us 1 over 27 to the 2/3. All right, and now I simplify it. So that's going to be 1 over, and that's going to be the cube root of 27, and then that's squared. All right, so once I made the exponent positive by moving it across the fraction bar, then I took this denominator here and I converted it to radical form. And so now all I have to do is simplify this, and we actually did that up here in part A. So this is going to be 1 over, and the cube root of 27 is 3, and then that's squared, and so I get 1/9. All right. All right, now let's look at this part D. So I've got 100 raised to the 6/4. So this is going to be 100, and what do you think I'm going to do? All right, that's right. If you guessed that I'm going to reduce the fraction, then you got it right. You see the 6/4 here, that will reduce. And so I just reduced the fraction. And now that I've reduced the fraction, now I'm going to convert it to radical form. So that's the square root of 100, and then that is cubed. And so now the square root of 100 is 10, and that's raised to the 3rd power, and so that equals 100. All right. Now let's look at this. Rules for rational exponents. All right. So in the previous section, we went over rules for rational exponent. I'm sorry, not rules for rational exponents, but rules for integral exponents, where the exponents were integers. Well, it's the same thing. Okay. So we're multiplying. We have like bases, so we add the exponents. If you're dividing and you have like bases, you subtract the exponents. This, we multiply them. And then this property and this property, they're pretty much the same. Basically what it's saying is whatever you have in parentheses, you raise each factor to that power outside the parentheses. And then these two properties were in the previous section also. If you have a fraction raised to a power, if you take the reciprocal of this fraction, it changes the sign of the exponent. So a over b to the -r is equal to b over a to the +r. And then this one, a to the -r over a to the -s is equal a to the s over a to the r. These two properties here are pretty much just telling you this is how you can make your exponents positive. Okay, and look, all they're doing, they just took this one, moved it across the fraction bar, see, the a to the s, and it changes the sign, and this one they move down to the denominator, changes the sign of the exponent. Okay. All right, now let's look at this. It says simplify, assume variables represent positive real numbers. All right, so for this one, well, what are we doing? We're multiplying. We have like bases, so we're going to add the exponents. So that's going to be x to the 2/3 plus 4/3. All right, so this is going to be x to the 6/3, which equals x squared. And there's your answer. All right, now let's look at the next one. So we've got x to the 4th times y to the 1/2, all of that raised to the 1/4. All right, so this property, that's that property a to the m, that's ab to the r equals a to the r, b to the r. We just raise each term to that exponent outside the parentheses. So that's going to be x to the 4th raised to the 1/4 times y to the 1/2 raised to the 1/4. So I just raised each term inside the parentheses to that exponent outside the parentheses. Okay. And now the property that we have is we have that property a to the r raised to the s is equal to a to the rs. We multiply the exponents. And so this is going to be a to the 4 times 1/4 times y to the 1/2 times 1/4. Multiply the exponents. And then we have what? A to the 4 times 1/4 is 1. So just remember, when you don't write an exponent, it's understood to be 1. Okay, see, that's a to the 1st, but we don't ever write the 1. And then that's going to be y. So I have no idea why I put a there. That's x. I guess I was thinking about this a here. I'm sorry about that. That's x. So that's x to the 1st, and then this one's going to be y to the 1/8. And there's your answer. Okay. All right, so let's look at the next example. So simplifying this one, I can actually do it a couple of ways. I can work this one a couple of ways. I can raise each term to that 3rd power. But what I like to do with this, when I have something in parentheses like this and it's raised to an exponent, I like to simplify whatever I can inside the parentheses first. Do you have to do that? No, you don't. I just think a lot of times it's easier to do that. So let's go ahead and just simplify what's inside the parentheses. So here you can see I have like bases with the a. So remember, if you have like bases, that means you subtract the exponents. And all of this is raised to the 3rd power. And so we have a to the 3/2 minus 2. Okay, so let's just real quick, 3/2 minus, get a common denominator of 2, that would be 4, so that's negative 1/2 to the negative 1/2, b to the 2/3. And then all of that is still raised to the 3rd power. All right. All right, so now we're right back to this like we have in this problem. I'm going to raise each term to that exponent outside the parentheses. And so this is going to be a to the negative 1/2 cubed times b to the 2/3 cubed. All right. And now that it's in this form, well, what does this mean? This means we multiply the exponents, right? We multiply the exponents. So what I'm going to do is, you see, like in this problem, how I went from this step and I showed this step. Well, I'm just going to go straight from here to here. I'm going to just do the multiplication in my head. So this is going to be a to the negative 1/2 times 3, which is negative 3/2. And then that's going to be b to the 2/3 times 3, which is 2. All right. Now, remember, whenever you're simplifying these things, you want your exponents to be positive. So I'm going to look at this as being over 1. I have a negative exponent on my a, so I need to move that across the fraction bar. And so that's going to give me b squared over a to the 3/2. And there's my answer. All right, so let's look at the next example. It says, simplify, assume variables represent any real number. All right, so I've got 64 a to the 6th raised to the 1/6. Right? So if I look at this, this is the same thing as the 6th root of 64 a to the 6th. All right. So for this problem, well, all we're going to do is take the 6th root of each term. Okay. So the 6th root of 64, well, that would be what? 2. And then the 6th root of a to the 6th, well, 6 goes into 6 how many times? 1. All right. So that would be a. Now, I want to ask you this. Is that our answer? I want you to think about it for a minute. Okay? So is that our answer? Well, and the answer is no. Okay? So the answer here is actually 2 times the absolute value of a. All right? So you might be thinking, well, what in the world's going on? I didn't mention anything about absolute value in this problem here, and we had the variables. Okay, we had variables. We were taking the 4th root. Okay, I didn't use absolute value here. The key to this is the directions. Assume variables represent positive real numbers. And if you remember what we talked about up here, remember when we were taking these square roots? Remember this problem, I told you if the index is even, then they want the positive answer. Okay? So that's exactly what's going on down here. Let's get back down here. Okay? So in the previous example, remember it said assume variables represent positive real numbers. Here it says assume variables represent any real number. So whenever we're doing these radicals, when this index is an even number, okay? Because see, when we convert this to radical form, the denominator is your index. When that index is an even number, we have to make sure that we get a positive answer. Okay? And since it says assume variables represent any real number, that means, and let me go ahead and erase this. That means that when we do this, you look at it and you say, okay, it represents any real number. Could A be negative? And the answer is yes, a could be negative. So we've got to put absolute value on the a to make sure it's positive. Okay? Now, if that doesn't make sense, or if you're kind of struggling through that, I think once we get finished with all 4 examples, I think it'll make more sense. So remember, whenever we're working these, and because of these directions here, assume variables represent any real number. If the index of your radical is an even number, you have to make sure your answer is positive. All right, so let's look at this one. So this is what? The cube root of x to the 9th. All right, so here 3 goes into 9, what, 3 times? So that's x cubed. So is that our answer? Is our answer x cubed, or should it be absolute value of x cubed? Well, this is our answer. Because remember what I said. You only have to make sure your answer is positive if the index, this number here, or this denominator, if the index is an even number. Then you make sure that your answer is positive. If you remember in that first problem we worked, I think it was part B, we had the cube root of negative 27, which is negative 3. If the index is an odd number, we don't have to worry about absolute value. Okay? If we're taking the cube root, the 5th root, the 7th root, the 9th root of a number, it doesn't matter. It can be positive or negative. The only time we've got to check is when the index is even. Okay? Now let's look at this one. All right. So let's convert this. I've got the 4th root of a to the 8th. All right. 4 goes into 8 2 times, and so that's going to be a squared. All right. That's a squared. Now, let me ask you this. Is that our answer, or do we need to put absolute value on it? This is our answer. Okay? Now, it's not confusing. Remember what I said. All right? Now, the one thing I want to make sure you did not hear, or you did not understand it this way, is never did I say, okay, so I know the index is even, right? But I never said if the index is even that you have to use absolute value. I did not say that. What did I say? I said if the index is even, you have to make sure your answer is positive. That's all you've got to think of, okay? So if the index is an odd number, you don't have to worry about absolute value. You don't have to worry about the answer being odd, or negative or positive. But whenever the index is an even number, you have to make sure your answer is positive. And if you remember, anytime you square something, that answer is always positive. You see that? Something squared is always positive. So the answer is positive. This a squared is always positive, so we don't have to worry about the absolute value. We don't need them. Okay? Now let's look at this one. So let's convert it. So I've got the 4th root of y to the 12th. All right? So first thing you think of, okay, do I have to worry about the answer being positive? Yes, because my index is even. So I've got to make sure my answer is positive. 4 goes into 12 3 times, and so that's y cubed. Now, is this my answer, or do I need absolute value? I need absolute value, because if you raise something to the 3rd power, could that be negative? Yes. And so since it could be negative, I got to put absolute value on it, because look at this. Negative 2 to the 3rd, see, raising something to the 3rd power, That's what? Negative 2 times negative 2 times negative 2, which is negative 8. Okay? There's a possibility of y cubed being negative, so I got to put it in absolute value. All right? So I hope that makes sense on that. All right? The only time that you've got to worry about putting the absolute value is when the directions say assume variables represent any real number and when that index is even. Then you've got to say, okay, I've got to make sure my answer is positive. And you could or could not have to put absolute value depending on, like this one, the index was even, but we didn't need absolute value because a squared is always positive. All right, let's look at this one. Product and quotient rules. So for any positive integer n in real numbers a and b, where b is not 0, the nth root of ab is the nth root of a times the nth root of b, and the nth root of a over b is equal to the nth root of a over the nth root of b. So all this is saying is that if you have some stuff multiplied or divided underneath a single radical, you can split it up into separate radicals. Or if you have stuff in separate radicals, you can put it back into up underneath one radical. All right. So basically, all this is saying is if I have a bunch of terms under the radical, I can just take the nth root of each one of those terms. Like in this case, I can just take the cube root of each one. I can take the square root of each one. I can take the fifth root of each one. Okay, so let's look at this. So we've got the cube root of 125a to the 6th. So all I'm going to do is I'm just going to take the cube root of each term. So the cube root of 125, that would be what? 5, because 5 cubed is 125. And then the cube root of this, 3 goes into 6 2 times. And so that's going to be a squared. And there's my answer. Okay. And once again, on this one, I mean, I know this index is odd, but on all of these problems, we don't have to worry about absolute value, do we? Because it says variables represent positive real numbers. So we don't even have to worry about it. It's telling us all the variables are positive. All right, now this one. So here I've got the square root of 3 over 16. Well, what's the square root of 3? Well, 3 is not a perfect square, is it? Okay. 16 is a perfect square. So what I'm going to do here is I'm going to split this up because one of them's a perfect square, one of them isn't. So let's split them up. I like to do that. Now, if all the factors underneath the radical are perfect squares or perfect cubes or whatever, I just take the square root, the cube root of each factor and write my answer down. But if I have one under there that's not a perfect cube or a perfect square, I like to just go ahead and split those up. So here I split them up, and so, well, the square root of 3, I can't do anything with that, so I'm just going to leave it. And then the square root of 16 is 4, and so there's your answer. Okay. Now let's look at this one. Now, I'm taking the fifth root of this. So the first thing I'm going to do is just scan real quick underneath here and see if everything's a perfect fifth root. Well, is 32 a perfect fifth root? Yeah. Does 5 go into 5 evenly? Yes. Does 5 go into 20 evenly? Yes. So I'm just going to take the fifth root of each term. So the fifth root of negative 32 is negative 2, because negative 2 raised to the fifth is negative 32. And then 5 goes into 5 one time, so that's y to the first, right? Y to the first, but when it's a 1, we don't write the exponent. And then 5 goes into 20 4 times, and so that's x to the fourth. And there's your answer. All right. All right, so now let's simplify this. Simplify, assume all variables represent positive real numbers. All right, so we don't have to worry about absolute value and all that good stuff. So whenever we're simplifying a radical, there's some rules that you have to follow, and they're basically what they are is you can't have, so a radical of index n is in simplified form when no perfect nth powers as factors of the radicand, no fractions in the radicand, and no radicals in the denominator. All right, so I don't know if that makes sense to you or not, but let me just explain it in terms of square roots, and then it applies for all of them. So in order for a square root to be simplified, the number underneath the square root cannot be a perfect square, and it cannot have a factor that's a perfect square. You cannot have a fraction under the radical, and you cannot have a radical in the denominator of a fraction. Okay, and then that applies the same for cube roots, fourth roots, fifth roots. So if you have a cube root, the number underneath cannot be a perfect cube, and it cannot have a factor that's a perfect cube. Okay, and then the same applies, no fractions and no radicals in the denominator. So let's look at this square root of 20, and let's work it out. And I'm actually going to work this out two ways. Okay, I'm going to work this one out two ways. I'm going to work it out a long way where it shows step by step everything that's going on. And then I'm going to work it out again of how you'll actually work it. My students, you'll actually work it the second way that I'm going to do it. It's leaving some steps out, but some of you know, if your teacher wants you to show every step, I'll show you in this first way that I work it. So the 20, is it a perfect square? No, the 20 is not a perfect square. Does it have a factor that's a perfect square? Yes. This is 4 times 5. Okay? 4 times 5. And then you remember that property that says I can split these up. Okay, I can split them up into two radicals multiplied together. And then we have the square root of 4 is what? 2, and then that's 2 square root of 5. And this would be your answer. Okay? Now, the way that I'm showing you how to work it shorter, it's not a lot shorter. It's just leaving this step out. It's basically what we're going to do. So let's do it again. So I got square root of 20. Okay? So just like here, I'm going to split it up into 4 times 5. And then what we're going to do, square root of 4 is 2. And then the 5, it has to stay underneath because 5 is not a perfect square. So it's just 2 square roots of 5. All right. So, I don't think any teacher is going to have problems with you leaving that step out. Some of them might, but I'm thinking the majority may not. All right. So let's look at the next problem. So here we got the square root of 24, x to the 8th, y to the 9th. All right. So let's look at this. So I've got square root of 24. 24 is not a perfect square, but it does have a factor that's a perfect square. So the 24 I can write as 4 times 6. All right. So remember, this index here is understood to be a 2. So does 2 go into 8 evenly? Yes, it does. So I'm going to keep the 8 as is. I'm not taking the square root yet. Okay, I'm just getting everything ready to do that. Now let's look at this. We've got an index of 2. Does 2 go into 9 evenly? No, 2 does not go into 9 evenly. So let's knock that 9 down to the next number. Let's knock it down to an 8. Does 2 go into 8 evenly? Yes, 2 goes into 8 evenly. So what I'm going to do is I'm going to rewrite this y to the 9th as y to the 8th times y to the 1st. So what I did is, you see the 24, how I had to split that up? That's the same thing I did to this 9 here. I had to split it up. See, y to the 9th, it has a perfect square in it, y to the 8th. So just remember, y to the 8th times y, and that's y to the 1st, is equal to y to the 8 plus 1, which is y to the 9th. All right, so I'm just simplifying that. Okay, I'm just breaking it up. And now we can go ahead and go through and take the square root of everything. So the square root of 4 is 2. All right. Now what about the square root of 6? Well, 6 is not a perfect square. It doesn't have a factor that's a perfect square. So the 6, it just has to stay underneath. And then I go to the next factor. 2 goes into 8 4 times. So that's x to the 4th. And then 2 goes into 8 4 times. So that's y to the 4th. And then if we look at the y here, 2 does not go into 1 evenly. So the y has to stay underneath. So that's times the square root of 6y. And this would be your answer. All right, so now let's look at part C. So I've got 9 over the square root of 3. 9 over the square root of 3. So for this one, I've got a radical in the denominator. And remember, for it to be simplified, you cannot have a radical in the denominator. So we need to get rid of it. So what I can do is I can multiply the numerator and denominator by square root of 3 over square root of 3. And why am I doing that? Well, because square root of 3 times square root of 3 is what? That's the square root of 9. And what's the square root of 9? It's 3. See, that gets rid of the radical. And, you know, you might be thinking, well, how can you just multiply a problem by something? Doesn't that just change the problem up? Well, yeah, sometimes it does. If you have a number and you multiply it by 2, it changes the number, doesn't it? But remember, I can multiply anything by 1 and get the same thing back. And isn't that all I'm doing right here? Isn't square root of 3 over square root of 3 is 1, right? So what I'm actually doing is multiplying this times 1. So it's not changing the problem up. I'm getting the same thing back. So when I do this, I get 9 square root of 3 over, and then square root of 3 times square root of 3 is square root of 9, and square root of 9 is 3. And then this simplifies, that cancels, and so I'm left with 3 square root of 3. And there's my answer. Now let's look at this one. So I've got the cube root of 3 over 5a to the 4th. All right, so nothing under here is a perfect cube. Okay, let's go ahead and split this up. So I've got the cube root of 3 over the cube root of 5a to the 4th. Now, what I'm going to do is look underneath the radicals. So I've got the 3. It's not a perfect cube. It doesn't have a factor that's a perfect cube. So let's go to the next one, 5a to the 4th. So 5, it's not a perfect cube. It doesn't have a factor that's a perfect cube. And then I'll look at the a to the 4th. Does 3 go into 4 evenly? No. But if I knock that 4 down to a 3, does 3 go into 3 evenly? Yes. So let's simplify that denominator. So that's the cube root of 3 over the cube root of 5 times a cubed times a. All right. So all I did, I just rewrote a to the 4th is a cubed times a. The exact same thing that I did up here in this problem when I rewrote the y to the 9th. All right, so this is going to give me the cube root of 3 over, all right, so that's going to be what? 3 goes into 3 one time, so that's going to be a times the cube root, and see this 5 and this a, it has to stay underneath. All right, so I've simplified up underneath all the radicals. Okay, I've simplified up underneath all of those. But now the problem that I have is I've got a radical in the denominator. So I've got to get rid of that radical in the denominator. So I'm going to multiply numerator and denominator by the cube root of, now, if you're following along with me and you're taking notes, all right, if you're taking notes, don't write this down just yet. Okay, I'm going to write in here what most students yell out in class. That. Most students say multiply by the cube root of 5a over the cube root of 5a. All right, this is wrong, but let's look at it. So if I multiply these two, let's just look at this part right here, just these two terms. If I multiply that, that is going to give me the cube root of what? 5 times 5 is 25. A times a is a squared. That's not a perfect cube, is it? You see that? What's the cube root of 25? Well, there's not one. What's the cube root of a squared? Well, 3 doesn't go into 2 evenly. And if I knock the 2 down, 3 doesn't go into 1 evenly. All right, so a lot of students, what they do is they think, well, I just multiply by whatever that is. And that's not the case. That works when it's a square root. You see how this radical, that index is a 2, that's a square root? That works with the square root. Okay, it works with the square root. It does not work with the cube root, a fourth root, a fifth root, a sixth root, and so on. So instead of looking at this and saying, well, what, I just multiply by whatever that is. Well, no, that's not true. It works with square roots, but let me tell you how you got to think about this, how you got to look at it. You look at this and you say, okay, what can I multiply to 5a so that I get a perfect cube? What can I multiply to 5a so that I get a perfect cube? Well, 5 times 25 is 125, and the cube root of 125 is 5. And then on this a, I need an exponent that 3 divides into evenly, right? So a times what? A squared is a cubed. You see that? And so this 3 will go into 3 evenly. So I'm multiplying by 25 a squared. Okay? So now let's write all this out. So if I multiply these two, that's going to give me the cube root of 75 a squared over the cube root 5 times 120. Oh, I'm sorry. Hang on. Left that a off. See, I'm writing this a down. Now let's multiply them. 5 times 25 is 125. A times a squared is a cubed, and that's the cube root. And so this is going to be the cube root of 75 a squared over a times, and the cube root of 125 is 5. 3 goes into 3 one time, so that's a to the first. And so that's going to be the cube root of 75 a squared over 5a squared. And there's your answer. And yes, I know, man, that looks tempting, canceling that 5 and that 75 and that a squared and that a squared. You can't do it because one's underneath the radical and the other one isn't. Okay? So there's your final answer. Now, as far as problems like this go, rationalizing denominator, you can search my channel. I have a video on just that, rationalizing denominators with variables. I work several problems in there like that if you need some more. All right, so now perform the indicated operation. We're going to be adding, subtracting, multiplying, and dividing these things. Now, what you've got to understand, this lecture is based on college algebra. What we're going over right now is in what a lot of college algebra books call section P, or I'm sorry, chapter P, which is the prerequisites. This in a college algebra class is meant to be a review. If you were in a regular algebra class, this section here would probably be split up into 4 or 5 sections. Okay? But this is a lecture specifically for college algebra. All right, so let's look at this. I've got square root of 20 plus square root of 5. All right, whenever you're adding and subtracting radicals, okay, whenever you're adding and subtracting radicals, the index of the radicals have to be the same, and what's underneath the radical has to be the same. So we want to do square root of 20 plus square root of 5. Okay? Well, the indexes are the same. They're both 2. But what's underneath the radicals is not the same. So we're thinking, well, we can't add those together. But if you look at this, square root of 20, we can simplify that radical, right? It has a factor that's a perfect square, the 4. So we rewrite the 20 as square root of 4 times 5 plus the square root of 5. And so this is square root of 4 is 2 square roots of 5. So there's square root of 20 simplified. And we actually simplified the square root of 20 earlier. Plus square root of 5. And now we're ready to add. See what's underneath the radicals? It's the same. The indexes are the same. And so now I can add them. All right. So what would our answer be here? Well, let me show you this, and I bet it'll make a whole lot of sense. What is this? 2x plus x. Everybody knows that's 3x. That's exactly what we're doing. It's just, see what's underneath these radicals are acting like these x's here. See, 2x plus 1x is 3x. 2 square root of 5 plus 1 square root of 5 is 3 square roots of 5. And there's your answer. All right, let's do this one. So we want to subtract. Well, guess what? Same thing. The indexes have to be the same, and what's underneath the radical has to be the same in order to add or subtract. So the indexes are the same. What's underneath is not. So we look at this and we see the 24. Hey, 24 has a factor that's a perfect square, right? 24 is what? 8 times 3. 8's a perfect square. Minus, and then I've got cube root. Let's see, 81 is what? 27 times 3. 27's a perfect cube. And I can't remember when I said 8, I can't remember if I said it's a perfect square or not. It's a perfect cube is what I meant if I did say squared. Okay. All right. All right, so now let's go through. The cube root of 8 is 2. The cube root of 3 and the cube root of x, they're not perfect cubes, so they just have to stay underneath. Cube root of 27 is 3. And then the 3 and the x, they're not perfect cube roots, so they have to stay. And so I have 2 minus 3 is negative 1. So that's negative cube root of 3x. And there's your answer. See? My radicals are the same now. All right. All right, let's look at this next one. I've got the 4th root of 4y cubed times the fourth root of 12y squared. Now, this time I'm not adding or subtracting, I'm multiplying. Well, in order to multiply, your indexes have to be the same. But what's underneath does not have to be the same. If you remember back, we had that property that said the nth root of a times b is equal to the nth root of a times the nth root of b. Well, you can also read it back this way. You just multiply what's underneath the radicals. All right. So, well, let's multiply. So I've got what? The fourth root, 4 times 12 is 48. Y cubed times y squared is y to the 5th. All right. And now, so we multiplied them, but now we've got to make sure, okay, can I simplify it? Well, does 48 have a perfect fourth root? Yeah, that's what, 16 times 3. 16 is 2 to the 4th. All right. And then this y to the 5th, that's what? Y to the 4th times y to the 1st. All right. 4 doesn't go into 5 evenly, so knock the 5 down to a 4. 4 goes into 4 evenly. And so now the fourth root of 16 is 2. 4 goes into 4 even one time, so that's just y to the 1st. And the 3 and the y, well, they're not perfect fourth powers, so they'll have to stay underneath the radical. And so that's times the fourth root of 3y. And there's your answer. All right, so let's look at this one. So we got the square root of 40 divided by the square root of 5. So on this one, first thing I would do, let's write it square root of 40 over square root of 5. All right. Now, one thing that might pop into our head first is, let's rationalize the denominator, right? And look, you could do that. You could rationalize the denominator. But I noticed that 5 divides into 40 evenly. And you remember that property, I can take this and write it underneath one radical, right? Remember we had the nth root of a over b is equal to the nth root of a over the nth root of b. And so I can go back this way too. So this is what? The square root of 8. See that? And so that's going to be what? Square root of 8, 4 times 2, which square root of 4 is 2, and then that 2 has to stay underneath, so that just gives me 2 square roots of 2. All right. All right, let's look at the next example. All right, so in this example, it says write each expression using a single radical symbol. All right. So we want to multiply these two. Okay, let's multiply the two. So we've got the cube root of 2 times the square root of 3. Now, when we're multiplying, we don't have to have the same thing underneath the radical. But what we do need is we need the same index, and we don't have that here, do we? So how do we go about working these problems? Well, what do we need? We need the same index, don't we? So what we're going to do is let's convert these to exponential form. Okay, convert them to exponential form. And then this is equal to, so what I'm going to do is I'm just going to go ahead and write this down, and then I'm going to explain it to you. So that's going to be 2 All right. So remember what I said. We've got to have our indexes to be the same. And remember when we were working the problems where we were converting from radical form to exponential form and exponential form to radical form? Remember, the denominator is your index, right? And what do I need? I need the indexes to be the same, so I'm just going to get a common denominator. So if this is a 6, remember how to build up fractions? 2 times 3 is 6, so I've got to multiply the 2 to the 1, so that's going to be 2. And then 3 times 2 is 6, so 3 times 1 is 3. And then what we do is we convert this back to radical form. So that's going to be the 6th root of 2 squared. So I just converted it back to radical form times the 6th root of 3 cubed. All right. So now this is what? The 6th root of 4 times the 6th root of 27, which gives me the 6th root of 108. And that's all they're wanting you to do there, is write that as a single radical. That's what they're wanting you to do. Let's look at this one. This right here, it's the same problem. Okay? It's the same problem. And I think what I'm going to do is I'm going to take this and I'm going to move it up a little bit. All right. So, well, let's do the same thing. Let's convert this to exponential form. Now here you got to be careful. This is the 4th root of 2y, so make sure you take that 2y and put it in parentheses raised to that exponent. Okay. So now, well, once again, let's get a common denominator. All right, so this would be what? 4, and this would be 3. And now we're going to convert it back to radical form. So that is going to be, let's see, that's the 12th root of y to the 4th times the 12th root of 2y. Now, that's 2y, and then all of that's cubed. Make sure you put that 2y in parentheses. And so this is going to be what? The 12th root of y to the 4th times the 12th root of 8y cubed. 2 cubed is 8, y cubed is y cubed. Now I can multiply these things together. So that is going to give me the 12th root of 8 y to the 7th. Y to the 4th times y cubed is y to the 7th. And so there's my answer. And look at this, the last problem. All right. Now, there's a simple little formula for this, but I'm going to work it out the long way, and then I'll show you the formula. I want to work it out the long way because that'll make you understand how the formula works, make you understand it better. And plus, if you forget the formula, then you'll know how to work it out. So you see this 2 to the 1/3. So that 2 to the 1/3, all I'm doing there is I'm going to rewrite that as an exponent. See? And then it still, of course, it still has this square root right here. Okay? And then what I'm going to do is I've got 2 to the 1/3, and I'm going to take this square root, and square root is the same thing as what? Raised to the 1/2 power. And then remember we have that property that says a to the m raised to the n is a to the m times n. Well, that's 2 to the 1/3 times 1/2, which is 2 to the 1/6. All right. And then I just convert that back to radical form, so I get the 6th root of 2. Okay. Now, the formula I want to show you is there's a formula that says if you have the mth root of the nth root of a, then that is equal to the m times nth root of a. So what it's saying is you just take the index here, multiply them together, and that becomes your new index. See, remember this index here is understood to be a 2. So look, what's 2 times 3? That's your 6 there. Okay. And yeah, you know, by all means use the formula, but I just wanted to work it out like this to show you, okay, to show you why it works like that. All right, so I hope this video helped. I would actually be surprised if anybody's still hanging around. If you are, leave something in the comments saying you hung around to the end. So hope this helped. Check out my other videos, and like I said, this right here, this is a college algebra. It goes through, it covers a lot of stuff in one section. If you want to see more specific and more detailed things on some of these concepts, go search my channel for it, so because I have it on there. So hopefully this helped. Check out my other videos. Give me a like, share, and subscribe, and thanks for watching.